Good morning, Mr. Joseph. Good morning.
Good morning.
Mr. Dillon? Dillon?
Yes, ma'am.
Dillon, can you hear me?
Yes, ma'am.
I can see that you're talking, but I can't hear you. Let me see if I have my volume. Oh, I had my volume turned way down. Try again. Dillon?
Hello.
Oh, hey, gotcha. And Joseph?
Good morning.
Good morning. I can hear you better now. I forgot I turned my volume way down. Who is Learning Center Tutors? Is that Miss Summer? Learning Center Tutors? Someone is signed in as Learning Center Tutors, but I don't know who it is.
Oh, I think that's me. I don't know why it's all like that.
That sounds like Autumn.
No, it's Abby.
Abby, hey. Well, that's funny. You are a Learning Center Tutor. I just don't know why it showed up that way.
Oh, I think it's because I might have accidentally logged in as my learning center, and I don't know how I did that.
Ah, that's fine. As long, I just wondered who it was.
Oh, okay.
Miss Grace? Miss Grace, can you hear me?
Yep.
Good morning.
Morning.
Mr. Aiden? Good morning, Aiden.
Good morning.
While we wait on just a couple more people, if y'all want to write down what I have on my paper, you may. Miss Ivy yesterday said, I can monkey see, monkey do, and get the right answer, but I really don't know what's going on. So I thought that was a fantastic question. I was going to try to answer that for her using what I've written there. Good morning, Miss Ivy.
Morning.
I'm about to make this make more sense today
Woohoo.
so that you don't have to monkey see, monkey do.
Okay.
I think there were, honestly, probably most of my time spent in calculus as a student, I was monkey see, monkey doing. It seems like you don't really understand something well until you have to explain it to somebody else, and thinking about how to explain calculus first time I ever thought it took a tremendous amount of effort, and really I think I worked harder that semester than my students did, just to be able to understand it well enough to explain the concept, not just the procedures. And I had a wonderful calculus teacher, so I know he went over this and over it, and maybe I got it at the time and then forgot it, or maybe I never did get that the derivative was just slope. And slope is important because it tells you how one thing is changing with respect to another. In business calculus, it might be how your profit is changing with respect to your number of units you're manufacturing. So what you have to think back to always, what you have to go back to when you're thinking, well, I can do it, but I don't get what it is at all, you have to go back to the fact that the derivative is really the slope formula. It's the change in y's over the change in x's as two x's get closer and closer. Now, when we use the symbol f prime of x, that's a good symbol. It's easy to write, but it doesn't really make clear that we're applying a slope formula to something. If we use the symbol dy over dx, then it's much more clear that that's a slope. That's a change in y over the change in x's. And I just graphed a little curve here. If we think about a marble rolling along this curve, or maybe it's part of a roller coaster. There's a car going up and then down and then up and further up. If you think about how fast the y's are changing with respect to the x, and again, y's are your vertical distance and x's are your horizontal distance.
Mm-hmm.
So if this is the path of a roller coaster, then dy over dx would give us how fast it's going up or down for each unit it's going forward. And sometimes that would be really, really steep. Right there, you're gaining a lot of vertical distance for every unit of horizontal distance you get. Up here, when the car stalls out for a split second at the top, you're not gaining any vertical distance for each unit that you travel horizontally. So that's why the slope of the tangent line right there is 0. And then as you come down, notice right there, the lines or the curve is about the same steepness as it was here. The y's are changing with respect to x at about the same rate, but I purposefully made this kind of flat part in the curve so that you could see right here, the x's are changing much faster than the y's. You're moving forward, but you're really not going up very much right here. So at its heart, you have to go back, you have to say, yeah, this symbol is convenient, but this symbol really tells us what we're talking about, the change in vertical distance with respect to horizontal distance. Now, if we have quantities that depend on time, we can say how fast is the y changing with respect to time and how fast is the x changing with respect to time, rather than how fast is the y changing with respect to the horizontal distance. So what we started with yesterday is a cone that was water was leaking out of at some constant rate. And like I said yesterday, if that water is leaking out at a constant rate, that doesn't mean the depth is decreasing at a constant rate. If you've ever watched water drain out of a funnel, then you know the closer it gets to the bottom, the faster it, when I say faster it drains, it sounds like I'm saying the volume is changing faster, and I'm not saying that. The volume is changing at a constant rate, but the height of the water or the depth of the water decreases faster near the bottom of the cone than the top of the cone. When you get down to that last few inches of water, it goes out quickly. Now, when we were using, let's see, we used, I just forgot the formula for volume of a cone. Pi r square h, I think, by V equals pi r square h, because pi r square, oh, you can't see that, sorry. Pi r square is the area of the surface, and then h is the depth of the water. So V equals pi r square tells the relationship between the volume, the radius, and the height. Since all of those things would depend on how long the water has been draining, we can differentiate each of those variables with respect to t. Now, what you said in your email, Ivy, was monkey see, monkey do. You said, I don't understand how we can just slap a dx over dt in there. Well, you have to remember that in implicit differentiation, for example, it would be kind of ugly to get that r by itself. So we can say, whenever I take the derivative of something with an r in it, and I'm differentiating with respect to time, then I have to have a dr over dt to indicate that I don't have r explicitly expressed, but I know it's a function of time. I know all three of these are functions of time. So when I write dv over dt, I'm saying volume is some function of time, but I don't know exactly what it is. So I have to have a dv over dt in my derivative. And then on the right-hand side, the pi is just a constant. What would it take to differentiate r square h?
Product rule.
Yeah, that's a product. So when I'm differentiating r squared, I'd not only get the 2r, but radius is some function of time. I just don't have it expressed explicitly. So I have to have the change in radius with respect to time as part of that derivative.
So it's like multiplying by the ugly prime.
Yes, exactly. That's exactly what we're doing. We're multiplying by the ugly prime. Now, with the product rule, it doesn't matter if you start with second derivative of the first or first derivative of the second, because it's adding. Apparently, I was thinking the second times the derivative of the first, and then plus the first times the derivative of the second. Well, what's the derivative of h?
Just h dh over dt.
If I was differentiating with respect to h, wait, that's not going to make sense. Yeah, if I was differentiating with respect to h, the derivative of h would just be 1. So the derivative of h with respect to time, rather than with respect to x, is still 1. But because h is a function of time that I don't have expressed explicitly, I have to include the factor dh over dt. So really, it's tempting to think this symbol is kind of as meaningless as this symbol, but it's a slope. It's a rate of change. It's how fast the volume is changing with respect to time, how fast the radius is changing with respect to time, and how fast the height is changing with respect to time. Even if this was constant, these two, r and h, would be decreasing faster the closer you get to the bottom of the cone. So if you wanted to give me this constant rate at which the water's dripping out, and you want to tell me how fast the radius is changing at some certain point, then I can tell you how fast the height is changing at some certain point. But these are factors. That's multiplication. I'm not just slapping a dB over dt on one side or a dr over dh. Let me try that again. dr over dt on one side. I'm saying if radius depends on time, but I don't have that relationship expressed explicitly, then I have to include in my derivative what we may have thought of before as just ugly prime, but I'm using a better symbol that actually has meaning in it now. It's twice the radius. Pardon?
Could you say then that anytime you're differentiating with respect to something that's not the variable you're differentiating, then you put the symbol?
Yes. As a matter of fact, if I had a minute, I'd show you that exact sentence in the book. That sentence is in 3.5, and you said it beautifully. If you're differentiating with respect to any variable other than itself, then you have to have that ugly prime as part of the derivative. But instead of ugly prime, we're going to write a better symbol for it that actually shows what that ugly prime represents.
Oh, okay.
So you said that well, Ivy. That's exactly right. We're implicitly differentiating with respect to time because we don't know what this explicit relationship is, or that one, or that one. But if you give me two of them, I can find the other one.
Okay, now I get it. Thank you.
Yay! I'm so glad. I'm so glad. I thought I could make it make sense to you. All right. Did I say try your best through 25? Is that what I said yesterday? All right. So you've watched a lot of even examples. My clipboard's going to annoy me. You've watched a lot of even examples. Let's do the odds that drove you the nuttiest. Ooh, I want to show you one other thing. I think in Momentum, I have this link printed, or this link posted in Momentum so that you can just click on it. But this website has some fantastic animations. You know how difficult it is for me to picture something happening, picture something changing. This website helped a lot with that. It shows one animation is something draining out of a cone, and you can see that the lower the water level, the faster the height changes, the faster the height decreases. There's another one with sand being poured out of a spout and landing in a conical pile. Same thing upside down, but the lower you are in the pile, the more spread out the sand is, and the less deep, the less depth is changing in the pile. But as you get close to the spout up here, I'm not sure this is going to make total sense. The height of the pile changes more quickly once you're near the top of the pile because it's covering less radius or less area. All right. So let me know if I do not have that link posted in Momentum. I will go in and post it. I'm pretty sure I do, but I'll go post it. Or if the website's changed somehow, I'll give you the new link. It may help you in some of these problems, like a ladder sliding down a wall. It helps to visualize that. Or a trough filling. It helps to actually see that happening. All right, enough of me. What odd problems do you want to see?
19.
19. 19 is one of the ones that I did not assign because we could spend the whole class talking about number 19. Since we're just trying to get the basics of the procedure here. I didn't assign the very hardest problems that would have taken us the longest to talk about. Now, I do think, now that you mentioned it, I think that I just said through 25 odd, and I apologize for that. I should have put this up here and said specifically what I want you to try is 15, 17, 21, 25. So if you lost sleep over, if you lost sleep over 19 or 23, then you can climb through the computer and whack me on the head, because I really didn't want you to worry about those two.
Okay, well, that's good.
I'm so sorry. I just glanced at it and said 325 odd. Go ahead and write down for tonight's homework, in case I mess up and say through 41 odd, that all I really want you to do tonight is 27, 29, 39, and 41.
Okay. So if I were to try 19, I just want to know if I was on the right track. Would you make 2 different formulas for the 2 different solids?
I think so, yes.
Okay, cool.
Yeah, you'd have to do that. All right, again, I apologize for giving you problems that I didn't mean to, but let's start with these. Does anybody need to see 1 through 13 or any part of 1 through 13? Going once. Going twice.
I'd like to see one.
Any, many, miny, mo. You've got to tell me one you tried and could not get. After you watch the video, one that you tried and couldn't get.
How about number 3?
Did you try it?
I did.
Okay, let's see. Number 3, the relationship that we're given is that y is the square root of x. And we have an a part and a b part. The a part says find dy over dt when x is 4. And if you want me to find dy over dt, you're going to have to give me dx over dt. And what we're given in that problem is dx over dt is 3. So this is saying find how fast the y's are changing when the x's are changing at 3, and we're not given units there. Maybe it's feet per second, maybe it's meters per hour. I don't know. But they're telling us how fast the x's are changing and asking us how fast the y's are changing. And since we know this is a half parabola, the rate at which the y's are changing is not going to be the same at all points on that parabola. The piece of parabola, the curve is steeper here than it is here. And that's why you have to be given at some particular point, find the change in y, because that's not going to be a constant. Even if this is constant, even if the rate at which we're moving forward is constant, the rate at which we're moving up is not constant. So I'm going to write that as y equals x to the 1/2. And then Aiden, what did you get as the derivative? With respect to time, not with respect to x.
I wasn't sure what to do on this one exactly.
All right, I got to ask you this, Aiden. I did number 6 on the video. Do you have that written down?
No.
Okay, then I'm not going to help you because you didn't watch the video.
Okay.
Somebody that watched the video got a question? You want to sign off after no examples, just a discussion this morning?
Can we do number 25?
Yeah, let's do 25. All right, here's what it says. And An air traffic controller spots two places at the same altitude converging on a point as they fly at right angles to each other. Oh, that said planes. I'm sorry, I couldn't read it well. An air traffic controller spots two planes at the same altitude. That's not good. They're converging on a point as they fly at right angles to each other. So let me just try to draw a picture of that. And one thing you might want to do in the homework is don't look at the picture in the book, because on the test, I wouldn't give you the picture. You have to kind of try to picture it yourself. So without looking at the picture in the book, I'm going to try to draw two planes that are converging to at right angles to each other. Let's see. Two planes converging on a point. Well, maybe I'll get some partial credit for a point. Two planes are converging at that point as they fly at right angles to each other. So one plane is going down to that point, and the planes are at the same altitude. So the other plane's over here, and they're converging at the point to the point at right angles. The picture in the book has the plane down here, but that's messing with my head because it doesn't look like the planes are at right or at the same altitude. You see what's bugging me about that? The planes are supposed to be at the same altitude and converging on that point at right angles to each other.
I think it's looking at them from the top.
Right. And that just kind of messes with my head. I may have to do it that way, or my picture is just going to look like their picture upside down, because I'm trying to make them look like they're at the same height. There's my right angle right there. Let's see. What else are we given? An air traffic controller spots two planes at the same altitude converging on a point as they fly at right angles to each other. One plane is 225 miles from the point. Since that's a distance, I can label one side of the triangle. Ooh, what's wrong with what I just did? Why does that 225 not go there?
The planes aren't at right angles to each other.
Well, that sentence, 225 miles from the point this is not 225 miles from the point, it's 225 miles from the other plane. So.
What?
I don't think my picture is going to work the way I have it drawn. I was trying my best to make it look like the planes were at the same altitude, but it's not going to work very well that way. I'm sorry. Looking at the planes from the top is going to be the best way to look at this, or from above. Here's one of my planes converging on that point, and then my other plane converging on that point. And one of the planes is 225. I'm going to label this one 225 miles from that point. And the other plane is 300 miles from that point. Now it bothers me that I don't have the longer side labeled the 300. You can see why I keep whiteout tape handy. All right, one of the planes is 300 miles from this point. One of the planes is 225 miles from that point. At what distance, or at what rate is the distance S between the planes decreasing? All right, distance between the planes would be that distance, and we're told to call that S. You can see that as time goes on, as this plane is moving down and this plane's moving to the left, the distance between them is going to get shorter and shorter, and air traffic control better intervene, or there's going to be a problem here at point O. Let me see what else I have. The plane is moving 225 miles. No, one plane is 225 miles from this point, and it's moving at a rate of 450 miles an hour. What symbol do you think we could use for the rate at which this plane is going? This distance is not a constant. That distance is not a constant because the planes are moving. So what if we called this horizontal distance of plane 2 from the point X, and we call this vertical distance of plane 1 from the origin Y? Then what symbol would say this plane is moving 450 miles an hour? I'll give you a hint. It's a rate, so it's a derivative. It has to be d something over d something. And if it's miles per hour,
dy over dt.
Yes, dy over dt gives us how fast this plane is moving. This plane is moving 450 miles an hour closer to that point. That tells you how fast y is changing. And then the other plane is moving 600 miles an hour. What symbol do you think should represent that?
dx over dt.
Yeah. Now, when you label a side of your triangle 225 and a side of your triangle 300, I kind of wish I hadn't written that, because that makes it look constant. It makes it look like y is always 225, and you have to understand it's not. That's just some particular point in time when y is 225 and x is 300. You got that? Any questions? That box of steps that we looked at yesterday said label all of the rates that you're given and use a symbol for the rate you're looking for. What's the rate that we're looking for? The question is, how fast are the two planes getting closer to each other? And we've labeled that distance S.
Are we looking for ds over dt?
Exactly. That's the change in S with respect to time. That's going to be in miles per hour also, because S is measured in miles and T is measured in hours. So we're looking for ds over dt when x equals 225, no, I'm sorry, x equals 300, and y equals 225. If I were to label my steps here, I would say step A is draw a picture and write symbols for everything that you're given. And then I would say step B is writing this statement that clarifies your goal. It tells me exactly what I'm looking for and exactly what I'm given at that point. And then step C would be write a relationship between X, Y, and S. Can you see any relationship that would apply to X, Y, and S in this scenario?
X squared plus Y squared equals S. I mean,
Yeah, that's just the Pythagorean theorem. X squared plus Y squared equals S squared. So my third step is write the relationship between all the rates that you know and the rate that you're trying to find. Or let me restate that. Write a relationship between all the quantities whose rate you know or whose rate you're trying to find. The fourth step is now differentiate both sides with respect to time. Well, X depends on time, Y depends on time, S depends on time, but I don't know explicitly what that relationship is. Actually, I know what two of those relationships are, but I'm looking for that third relationship. So when I differentiate a term with respect to time, I'm going to have a dx over dt or dy over dt or ds over dt as part of that term. When I differentiate the x squared, it's 2x. And then since x depends on time, but I don't know explicitly how, I'm going to have the factor dx over dt. In a minute, I'm going to end up putting 600 because actually I do know the rate at which x is changing with respect to time. The derivative of y squared is 2y times the rate at which y is changing with respect to time. And the derivative of s squared with respect to time is 2s ds over dt. Now, Miss Ivy, do you feel less like you're just slapping symbols somewhere now?
Yeah.
Good, 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 good. All right, this is the guy that we're solving for, the guy that we're trying to find. So in order to solve for this, you have to give me an x, which you did, and a y, which you did, and a dx over dt, which you did, and a dy over dt, which you did. What's the only variable in that equation that you didn't give me? Other than the one I'm looking for.
S.
Yeah, you didn't give me an S. Well, how am I supposed to know what to plug in for S when X is 300 and Y is 225?
Could we use part C to find S?
Absolutely. We'd use the Pythagorean theorem to find S. And this is, again, at one particular moment in time. This distance is changing, this distance is changing, and this distance is changing. But at the moment in time when X is 300 and Y is 225, we can find the distance between the planes with the Pythagorean theorem. So I'm going to call this E when X equals 300 and Y equals 225. S would be the square root of 300 squared plus 225 squared. And I don't know if that's a Pythagorean triple or not. I think I have this one written down somewhere. Ooh, no, I didn't bring my odds with me. So let somebody punch that on the calculator real quickly.
375.
375, so it is a Pythagorean triple? Is that what you said?
Mm-hmm.
Everybody agree?
Yep.
Okay, so now I have everything I need to solve for ds over dt in this equation. I'm going to put all 5 values that I know into the d part and say when x is 300 and dx over dt is 450 and y is 225 and oh, that's right. No, I put the wrong number in for dx over dt. 2 times 300 times 600 plus 2 times 225 times 450 equals 2 times 375 times the thing I'm looking for. Whew. Y'all, mirror image is so difficult for me. I can't move that camera in the way that I want it to make that visible to you. Whew, that was hard. So hard for me. What's that left-hand side? 1836 with 4 zeros on it? Plus 202,500. I hope somebody else is punching this with me and can tell me if I've made a mistake. Is anybody else punching it and got 750?
That's
You
right.
got it.
Okay, cool. So our answer, we are not going back to this air traffic controller and saying ds over dt is 750. You might just slap us because people are about to die. So what would be a more appropriate thing to say to this air traffic controller?
Miles per hour.
Okay, that is the units on the 750. It's miles per hour, but still I wouldn't go to the air traffic controller and say ds over dt is 750 miles an hour. I'd use some words. What words would make sense of what that ds over dt represents?
The planes are converging at each other or on each other at a rate of 750 miles per hour.
Awesome. And I like the word you use, converging there. The planes are converging on each other at the rate of 750 miles an hour. Now, is that 750 miles an hour constant? Is that the rate at which they're always getting closer to each other?
No.
No, that's just how fast they're getting closer to each other at the point where this plane's 300 miles away and this plane's 225 miles away. As they get closer to this point O, they start converging on each other faster and faster. The length of the hypotenuse is going to get smaller and smaller as these two planes get close to that point O. So I wouldn't just say the planes are converging and we would want to say on each other, not on point O. $750 miles per hour. I wouldn't just want to give that. I'd want to say when first plane is 225 miles from the point, and I almost didn't leave myself enough room here, and second plane is 300 miles from the point. At that moment in time, this is how fast the planes are getting closer to each other. Any questions about that one?
I have a question about 450 and 600. How come they're positive? Weren't they supposed to be negative in the beginning?
Oh, I love that you said that. So good. I made two mistakes that happened to cancel out, and that happens sometimes. You make one mistake and then you make another mistake and you still get the right answer. That happened on this problem, but it may not happen on another problem, so I need to be aware of it. The two mistakes I made here is this tells me how fast Y is shrinking. This tells me how fast X is shrinking, but they are both shrinking. So technically, you're absolutely right. I should have used negative 450 and negative 600. It wouldn't have changed the answer here. It wouldn't have changed S because I'm going to square both the X and the Y. And so S is still going to be positive. If I'd said X is negative 450 here and dx over dt is negative 650 there, then where would that, then I would have come up with a negative 750, and that just means this distance is getting smaller also. I still wouldn't write my answer as negative 750. I'd write my answer as the distance between the planes is decreasing. Or another sentence that means the exact same thing is the planes are converging on each other. That implies the distance between them is getting shorter. So I'm very, very glad you said that. Technically, I should have had negative here, and that answer is negative. All right, what else? We have about 6 more minutes. So everybody, at least everybody who watched the video, where are those problems numbers written down? It's under this paper. No, it's not. Well, here they are. So everybody else was able to get 15, 17, and 21. Is that correct?
I wasn't able to get some of them, but I want to go back and look at it now that
Okay.
I know what I'm doing.
Okay, that's fair enough. That's what I like to hear. Not, I just want to watch you do it, but I want to go back and think about it some more. Like I said, this is the only 4 problems you have in tonight's homework. And I worked these 5 examples on the video. These are, I think, a little bit harder. It's a little bit more difficult to picture what's going on. They don't just, actually, most of them do still involve a right triangle, but it's a little bit more difficult for me to imagine what's happening to this person's shadow as they walk closer and closer to the pole, or in another problem, as they walk away from the pole, what's happening to their shadow as this ladder is sliding down the wall. this distance is getting smaller and that distance is getting smaller, but the ladder's not going to change lengths as it slides down the wall. And this one, as a player runs from one base to another, how is his distance from home plate changing? It's just things that are more difficult for me to visualize, and you may not have any trouble with it at all. But if you do, check out this website that I posted in Momentum and actually watch the things changing. Animations of the things changing will help you visualize it better. All right, if you don't have any other questions, watch these 5 examples on the video and then try those 4 problems. If I can't find some good problems to put in my labs, I mean, I can't really give a multiple choice related rate problem. There's too much to it. So every once in a while, I may say, send me a picture of these 4 problems rather than me just putting problems in them in my math lab like those. If I do that, if I don't find any problems in my math lab and I just want you to send me a picture, I'll send you a remind that says, hey, tomorrow just send me a picture of these 4. Does that make sense?
Okay, so what are we doing for my math lab today then?
Let me look in my math lab and see if I can find any problems that I want to put in there for your 6 problems tonight. Or since these problems are so long, I could just pick 3. But let me say this, Ivy. At this point, I haven't looked to see if there's any problems I want to put in my math lab. But as soon as I do, I'll send you a remind that either says there are now problems in my math lab for you to do before tomorrow, or I'll send you a remind that says, I just want you to send me a picture of these tomorrow.
Okay.
Yeah, I'll send you that information. I'm just not sure right now. Depends on what I find in my math lab. Okie dokie.
Artichoke.
Okie dokie artichoke. All right, I'll see y'all tomorrow.